Hello and welcome to part 4 of QED Stata 2. So on a question here about a normal distribution with a mean and standard deviation that we've just found, what percentage of values are greater than 8? So let's just grab the mean and standard deviation from here. So that's these figures. Just take it off and paste it into a friendly whiteboard over here. A bit bigger so we can actually see what's going on. And then in time-ordered fashion, the value of x we're interested in is 8. So he wants to know how many values are bigger than that if that's the mean and standard deviation. So you want a z-score to start with. So z-score is the 8 minus the mean divided by the standard deviation. Okay, so one thing you can do is you get a calculator out. However, there's another way of doing it, which is this. We can go back to our friend stata here, and we can tell stata that we want to work out the z-score by using the display command. Now, if you put di, that basically just displays whatever result, the result of whatever you put in on the screen. So basically it means you can use stata as your calculator. But it's better than that because it's already got those numbers we want to use in there. So if I put in here 8 subtract, instead of typing in this thing here, it's already saved in stata, and it's saved in what's called the results. And if you look back at the summarize help file, which I think might still be open, you'll see down here, these are the things that are saved. So I'm going to need the mean, and I'm going to need the standard deviation. I'm going to need the number of observations in a minute. So I can use all those in the display thing by saying, let's have 8 and subtract from that the mean, like so, and then divide by the standard deviation. I'm using the mean and standard deviation. I should have just redone that command to make sure that the numbers are in the memory. I managed to lose that from the history. Yeah, so this time it's come out as 1.35. So that's my Z number, 1.3589775. So I can grab that. It didn't work the first time because I've managed to do another command. The problem with the R results is that once you do another command, it rubs them out. Can't find my whiteboard. What? Disappeared from it. There's the answer for that. That's the z-score. Next I want to make that a bit bigger. This is the z-score, so now he wants to do is look up in tables what values of z, or what percentage of values of z are less than that. You can look up in the tables. That's something else you can look up in stata. Hang on. So here, I'm going to bring back this command, and if I put normal around there, like in brackets, that's telling me that, that's like looking up in the normal table, it's telling me that 91% is less than that. So then if I build it up bit by bit, I need to have oops, 1 minus that, so only 8.7% is greater than that. And then the final answer I want, oh, that's the final answer, is 8%. So it's about 8.7%. %, above 8. So I'd expect that there'd be about 8.7% of households would have more than 8 people if it was normally distributed. Now what you need to do is, once you work that out, you want to actually count how many actually are in the actual data above 8. So in the command window, because I don't want to store this is just something I'm doing as a test now, I don't want to store it in the processing, I'll just go do this. And this command just counts how many rows satisfy this condition. So it counts how many rows, how many observations are there with a household bigger than 8. So copy that, put it into the command window just to carry it straight away. 114. So how does that compare to 8.7? Well, I have to compare the 1.1. I'd have to compare this to how many observations you have, which, remember, when we described it, was 1510. So again, display 100 times 114.1510. So 100 times 114 over 1510 will give me the percentage, which comes out as 7%, rather than 8%. So it's not a very long way from the 8.7% calculated. So if it was normally distributed, you expect about 8%, 8.9, 8.7% above that figure of 8. You've actually got 7.5%. So that's these ones here. So it's actually slightly fewer. From the graph, it looks as though there's more than you'd expect coming out to the right, but it's actually very slightly fewer. It's hard to judge when it's that close by eye. So it shows that it's not very far away from a normal distribution. Okay, and then this is where we go. I can put the normal thing in. So first of all, just to mention, yeah, this is what tests of normality are based on. So when you run tests of normality later on, what it does is it takes lots of regions and it works out how many would we expect between here and here, here and here, here and here, if it was normally distributed using the z-scores. And then it counts and compares how many there actually are and says, okay, is that close enough for it to be normal? But you'll see those tests later on. For now, and another easy thing you can do is to add this option to the histogram. Oops. And that just does this. So it shows you roughly what the balance of it should look like if it was normally distributed. In actual fact, you might like to think, well, why there are so many more everywhere than we expect to be on this line. And it's because they're only in whole numbers. So if these whole numbers were spread out more, then they'd be filling up this line more closely. So that gives you an idea of how to compare it with a normal distribution. And as it's saying here, that this positive number for skewness, when this is a positive number, it means it's going to have that shape of being slightly more skewed out to the right. That's what we call a positive skew. You can remember it by thinking that if you can't remember which one's positive and negative, then what I recommend is that if you turn this onto its side like this, it gets a P shape here. So it's positively skewed. P for positive. If it doesn't do that, it's negatively skewed. Okay, so now we can go on to look at some other variables and do similar things, but for now, thanks for watching.